We bring to you from Vyas Certification this portion of NCERT discussion, class 11th chemistry, and we are talking about a unit in organic chemistry. Yes, the very favorite, some basic principles and techniques of organic chemistry. It's a very conceptual, very fundamental, essential chapter of great importance in understanding the basics of organic chemistry. I repeat, doing it, studying it from NCERT for the first time can be suicidal. You may be quite misled into misunderstanding a number of concepts, but in case you have understood the concepts from an independent source, NCERT is a great place for revision, and because of the nexus between authorities, it makes it compulsory also. So, let's start taking a look, and there comes your first question. What are the hybridization states of each carbon atom in the following compounds? Fascinating. And we have number of following compounds. CH2, CO, HCH, double bond C, double bond O. Let us not forget a simple table. And what is that? Okay, number of bonds formed, and this is element. In organic compounds, you would find if you have carbon would have 4 bonds and number of lone pairs on an atom. It's a very useful table. Please note. So carbon atom would not have any lone pair of electrons, but it would have 4 bonds. Like you can see, this carbon has 1, 2, 3, 4 bonds. Can you see that? This carbon has 1, 2, 3, 4 bonds. So carbon always tends to form 4 bonds only as long as there is no charge present on the atom. Right? So this is uncharged. There is no positive or negative charge. In that case, carbon would form 4 bonds and no lone pairs. Nitrogen will form 3 bonds and 1 lone pair. Oxygen would form 2 bonds with 2 lone pairs, and all halogens FCl, Bri would form only 1 bond and they would have 3 lone pairs. This is true for all reasonable compounds in organic chemistry. Right? Perfect. We'll use this information. You're supposed to remember this table. You're supposed to have memorized this information. Using this, I'm trying to draw their full structures. This first molecule is called ketene. Sounds like kitty party. It's ketene. And then you have CH3, CH3, CH double bond, CH2. I've just drawn 2 compounds. There are 3, 4, 5. There are 2 more. Let me draw all of them actually so that you can take a good look at them. Then we have CH3, CH3, C double bond O, and then again we have CH3. Right? Lastly, last 2 compounds also. Let me just first solve them and then I'll go to them. Agreed? Fine. The first one. Now, how do I decide hybridization? For deciding hybridization also, there is a trick. And what is that? Just count the number of sigma bonds plus lone pairs. Sigma bonds plus lone pairs is equal to what we called as steric number. And between 2 atoms, please remember, there can be only 1 sigma bond. All the extra bonds are pi. So 1, 2 and 3, sigma, sigma and sigma. There is only 1 sigma bond each. So this carbon has 3 sigma bonds, right? And does this carbon possess any lone pair of electrons? No. So steric number is 3. And with every steric number, a hybridization is associated. So what would be the hybridization? Let me again give you a small chart. If you have steric number 4, 3 or 2, accordingly you would have hybridization sp3 or sp2 or sp. Wow, that's the way. That is the way, my dear. So what do we have? We have this carbon as sp2 hybridized. What about this one? Sigma and sigma. Only one bond is sigma. Please remember, these are pi bonds. Actually, the upper bond is pi bond. There is nothing called as upper or lower bond. You can choose any one of them. Any one of them is sigma, the other one is pi. We don't care about pi bonds. So for this carbon, if I count for this carbon, sigma bonds are 1 and 1, 2. Lone pair 0, the steric number is 2. This means that this carbon is sp hybridized. See, steric number 2 means sp. So we say this is sp hybridized. sp2 and sp. That goes, yeah, there goes your first question. What about propene? Let's take a look. 1, 2 and 3. sp2. Done? What about the other one? This carbon, 1, 2 and 3 again. Wow. So this also would be sp2, very much. What about the third one? 1, 2, 3 and 4. Wow. This is sp3? Yes, this is sp3. sp3, sp2, sp2. These are the hybridizations of each carbon atom. Let's take a look at the next one, the third one. The name of third one, actually, there's a common name. It's called acetone. Acetone. Yes, this is acetone. Lovely molecule. A very popular nail polish remover. In case you use a nail paint, it is used for removing old nail paint and as a thinner for nail paints in general. Very popular compound, sweet smelling. See this carbon, 1, 2, 3, 4. So this carbon is sp3. 1, 2, 3, 4. So this carbon also is sp3 hybridized. Can you see that? Yeah, we can. What about the other one? The middle one. 1, 2 and 3. That means it should be sp2. Steric number 3 means sp2. So this is sp2 hybridized. There we are. Got it? Got it. Let's draw 4 and 5 and see. We have H, CH double bond, CH, CN. Oh wow. And then we have C6, H6, the very popular benzene. H, H, H and H. This is the lovely benzene. And this is acrylonitrile. Common name, very popular compounds these are. How do we get the hybridizations? Not very difficult. All we need to do is look at this carbon again. 1, 2 and 3. 3 sigma bonds, carbons not normally, they don't possess lone pairs anyways. This is sp2. This carbon 1, 2, 3, again sp2. This carbon 1 and 2. Wow, it is just sp. Yes, it's just sp. What about these? In benzene, all carbon atoms are similar actually. 1, 2 and 3 bonds, and this is it. So this carbon is sp2. As a matter of fact, all the carbon atoms, this, each of these 6 carbon atoms is sp2 hybridized in benzene. Indicate the sigma and pi bonds in the following molecules. I am being offered certain molecules and I am supposed to count the number of sigma and pi bonds in them. How do you think would you be able to do this? Well, the simplest way is, first of all, draw their structures. And from their structures, you would be able to count the number of sigma and pi bonds. So let us draw C6H6 structure. Is benzene? No. No. It could be and it need not be. How? Let me show you. See, the simplest assumption of NCERT, of course, is it is benzene. If I assume that, my dear, this is what I would draw. This is the structure of benzene, but they have not written that this is benzene. So as per the question, it is one possible answer, but it is not the unique answer. Often, like first let me just finish this. Na? Sigma CH, how many? 1, 2, 3, 4, 5, 6. 6 bonds. Sigma CC, how many? 1, 2, 3, 4, 5, 6. So overall you have 12 sigma bonds. Fine. And 1, 2, 3, you have 3 pi bonds. Is this an answer? Yes, that is the official answer. Benzene. Is it a unique answer? No. Why? If you are just writing C6H6, my dear, I could very well draw more structures which also have the same formula C6H6. Like this. Just take a look at this very funny structure. If you count 1, 2, 3, 4, 5, 6, you have 6 sigma CH. Of course, each hydrogen forms only one sigma bond, so there has to be 6. There has to be 6 bonds only. Sigma CC, 1, 2, 3, 4, 5, 6, 7. And pi bonds, pi CC, 1 and 2. So you have 13 sigma and 2 pi. And my dear, this also has a formula C6H6. So if a student writes this, as per NCERT, the student will be confused because NCERT does not give this answer. So you may be confused, are you correct or not? You are very much correct. So that means this is not the unique answer? No. And that is why I often make comments about NCERT. NCERT is a confusing book. They speak half-truths, incomplete truths, and they confuse the students. But for your information, this is totally correct. There is no problem with this. Not just this, I appeal to you, exercise your imagination and just try drawing more molecules. Can you? Allow me to present one more, the very famous prismane. What is prismane? Prismane is a fantastic molecule. What is this? This is not a molecule? Oh, of course it is not. But then, allow me to just finish drawing this. This is the structure of prismane. This is hydrogen atom, of course. There are no pi bonds. There are no pi bonds, my dear. 1, 2, 3, 4, 5, 6, 7, 8, 9. Please note, this is one bond. I'll just change the color to make sure that you understand this. This is one bond, and behind, this is outside, in third dimension, and behind there is another bond. This is one CC bond. So there are 9 CC bonds. There are 6 CH bonds, and there is no pi bond. Okay, so you have 15 sigma and 0 pi, and that also very well could have been answered to the first question. How many sigma and pi bonds in C6H6? It could be this, could be this, could be this. And if you allow me, I can keep on going and I can keep on presenting you with molecules having formula C6H6, having different number of sigma and pi bonds. There we are. And each of them is correct. Each of them is correct. This may be the official answers, but answer, and these are as per chemistry and science. Each of them is correct as the other one. The second molecule also is equally controversial. Let's take a look. If you write down the formula of C6H12, you would notice there is a problem. What is the problem? You can draw a cyclohexane like this. It has 12 CH, 6 CC bonds, 18 sigma and no pi. Is this possible? Yes. You could also draw cyclohexene, not cyclo, simply hexene, like this. This has 17 sigma and 1 pi bond. Which one are they asking? They have not specified. They printed a question and ran away without worrying about the idea that it could have had more than one answers. But yes, it very much can, as you can see. Which is correct? Both are correct. Anyone is fine, good enough. This is the second molecule. What about the third one? Let's take a look at CH2Cl2. This is CH2. This is a very simple molecule, 4 sigma. There is no pi bond and nothing to abuse NCERT about. This is clean. What about allene? CH2 double bond C double bond CH2. This is allene. Allene, if you count 1, 2, 3, 4, 4 CH bonds, 1 and 2 CC bonds, and pi bonds 1 and 2 again. So you have 6 sigma and 2 pi bonds. Good enough. Then we have nitromethane, CH3, NO2. Now you must learn how to draw NO2 group properly. Very important. This is the structure of nitromethane. And then you have HCO, NHCH3. Fanciful. N-methyl formamide. Now, can we count sigma and pi? Who can stop us? Of course we can. And what would that be? Let's see. 1, 2, 3. 1, 2, 3, 4, 5, 6. 6 sigma. And 1 pi bond, there is only 1 pi bond. 6 sigma and 1 pi, don't worry about charges. 1, 2, 3, 4, 5, 6, 7, 8. This is only 1 bond. 8 sigma, 1 pi. All right, bhai? Yes. These are the molecules. Write the bond line formulae for isopropyl alcohol. Okay. There are 3 items. Isopropyl alcohol. Now, how do you write down bond line formulae? In bond line formulae, you assume that every line is CC bond. Double bond means double line. Triple bond means 3 lines. All the heteroatoms like nitrogen, oxygen written clearly. Every corner is carbon and hydrogens are eaten away. You assume that all the remaining valencies would be satisfied by hydrogen. This is the way we write down bond line. In isopropyl alcohol, first of all you have isopropyl group. Now this would be the isopropyl group. 1, 2, 3 carbons, isopropyl, and alcohol means I have OH here. This, my dear, is isopropyl alcohol. First one. Then we have 2,3-dimethyl butanal. Now I catch the word but. But means 4. 1, 2, 3, 4. 4 corners means but. Butanal. Al means aldehyde. So let me draw an aldehyde at the corner. And this gets the number 1. The locant 1. 2, 3. 2, 3. Dimethyl. So let me draw methyl groups. 1 line each, that's it. 2, 3 dimethyl butanal. Heptane 4-one. Hept means 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 4-one. This represents ketone. Let me draw a ketone here. Right? And I'm also writing down locants, which is not necessary for presenting the final molecule. This is just for your information. But this is heptane 4-one. Easy enough? Very easy. You must learn the names of functional groups, my dear. Which is aldehyde, CHO group. Suffix is al. Which is ketone, C double bond O group. Suffix is -one. You need to remember these names and the nomenclature system, of course, in order to solve this question. Give the IUPC names of each of these. Lovely. How do we give the IUPC name? First of all, we decide the parent chain. In this case, the parent chain is the lovely fat benzene. And 1 dash, 2 dash, 3 dash. Dash indicates it's a side chain. So what is that? Well, it is propyl. So this would be simply propyl benzene. Parent chain is benzene. It is written at the end. It is the prefix is the side chain. So this is propyl benzene. That's it. As simple as this. Simple propyl benzene. B part, you have cyanide. Now cyanide has a suffix nitrile. And the very important part is, when you say nitrile, carbon of cyanide is counted as a part of main chain. So I would say that this is the main chain. 1, 2, 3, 4, 5. You've counted that carbon, you have put number 1. That is the rule. This is how we have to count this. Please remember. 5 carbons. So that has to be pentane. But there is cyanide here. Let's call it nitrile. So this is pentane, nitrile. Wow. And there is a side chain, methyl, at number 3. So this is 3-methyl. It is 3-methyl pentane nitrile. Right? Right. What about C? Let us see. Well, we have one. First of all, the longest chain is the main chain. So let us take the longest chain as the main chain. Now numbering can begin from this end. The numbering can also begin from this end. What is the correct way to number? The point of earliest difference. Wherever there is branching earliest, wherever you find that the branching appears at the earliest point, like in this case, if I number like this 1, 2, 3, 4, 5, 6, 7, first branch appears at number 2. But I could have solved it, I could have numbered it otherwise also. Yes, in case you number it as 1, 2, 3, 4, 5, 6, 7, that is an alternate way of numbering it. This would not be correct because the first branch would be at 3. First branch at number 3, first branch at number 2, yes. So red numbering is wrong and the purple numbering is correct. So what do I get? I get, this is 2,5 dimethyl heptane. You get 2,5 dimethyl heptane. Watch the next one. It says, well, first of all, get the main chain. Main chain is this 1, 2, 3, 4, 5, 6, 7. So this is 3 bromo, 3 chloro heptane. 3 bromo, 3 chloro heptane. Right? This is where we are. What about E? Don't count this. This is chlorine. That is not a part of main chain. This is side chain. Can you identify the main functional group? Yes. Cl, or what is this? COH. Oh my God. This is aldehyde. Yes, it is aldehyde. Aldehyde has higher priority. So naturally, the suffix al would be used. And 1, 2, 3. Count this carbon also. This is 1, 2, 3. So this is propanal. Yes. At 3 chloropropanal. Easy enough? Totally. Perfectly. Beautifully. Fine. What about the last one? This looks like an alcohol. Alcohols have suffix -al. Yes. Count the carbon chain. This is the carbon chain. 1, 2, 3. It should be CH3, not CH2 actually. So, this is propane 1-ol or 1-propanol. Which one is correct? Both are correct. It's okay. It's up to you how you write it. Propane 1-ol or 1-propanol. It has a common name also. Sometimes old people used to call it N-propyl alcohol. But these are the IUPC names. Which of the following represents the correct IUPC name for the compounds concerned? And what do we have? We have 2,2-dimethyl pentane, okay, or 2-dimethyl pentane. Let's see. Now, if I'm drawing pentane, this is pentane. And if there is dimethyl, 2,2-dimethyl, 2,2-dimethyl, 1, 2. This makes sense. if I'm saying dimethyl, where are those methyl groups? I could have had one methyl group on one carbon, the other methyl group on the other carbon also. So if there are dimethyl, if I have two methyl groups, I should have two different numbers, two different locants. One locant for one methyl and the other locant for the other methyl. If I just write down one, that is not sufficient. If both the methyl groups are present on the same carbon, I am supposed to write it twice. So this is the correct name and this is the wrong name. Right? That's the rule. What about the B portion? Let's see. 2,4,7 trimethyl octane. 1, 2, 3, 4, 5, 6, 7, 8. This is octane. And 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. This is octane. I'm drawing octanes twice. 2,4,7 trimethyl. 2, 3, 4, 5, 6, 7. This is 2,4,7 trimethyl. And 1, 2, 3, 4, 5, 6, 7. Actually, if you look closely, both these compounds are the same. We have just numbered them differently. In what way? Well, take a look. 1, 2, 3, 4, 5, 6, 7, 8. Octane, 2, 4, 7 trimethyl. This is the way we are writing it. What about this? If I number it as, like I'm saying, this is 1, 2, 3, 4, 5, 6, 7, 8. Now this looks like 2, 5, 7 trimethyl. Are they really different? Just number it backwards and check. If you number that backwards, you would discover a different story. Let's see. If this is 1, 2, 3, 4, 5, 6, 7, 8. Oh my God, what is this? We have 2, 4, 7 instead of 2, 5, 7. Now you can also get 2, 4, 7 and blue numbering is correct and the purple one is wrong. Why? Earliest point of difference. The locant should be as small as possible. That is the rule. So if I have 2, 4, 7 or 2, 5, 7, 5 is bigger than 4. So I say this is wrong and this is right. This is right. Got it? Locants have to be minimum as far as possible. The third option. 2-chloro-4-methyl pentane. So let me first draw pentane for you. This is pentane. I am drawing two pentanes. 2-chloro-4-methyl or 4-chloro. Okay, so it's more like what would be the way in which I number this? Should it be like 1, 2, 3, 4, 5? Or should it be opposite? 1, 2, 3, 4 and 5. The blue numbering or the red numbering, which is the correct one? What is the rule here? And the IUPAC rule is all the prefixes have same order of priority. So which has higher priority? Chloro or methyl? All the prefixes have same level of priority. The only difference lies in whichever appears first. So you count from both the ends. If I count from this end, Cl appears at number 2. If I count from the other end and if methyl appears earlier than that, you can't actually appear earlier than number 2, but nonetheless. Then in that case, whichever appears first, whichever has the lesser locant, that is chosen. Unfortunately, that rule does not apply here because if I go from this end, Cl is number 2. If I go from red end, I find methyl also is number 2. So it's 2, 4 this way, opposite way also is 2, 4. So if the number of locants or if the locants are exactly the same, if I count this way or that way, then we come to the last rule and that is the alphabetical order. Whichever is earlier as per alphabetical order, that should have the lesser locant. So chloro and methyl, if you see, chloro is alphabetically earlier. So that should have a lesser locant. 2 is correct and 4 is wrong. Oh my God. So ABC, only the first options were the correct ones. Yes, it seems so. The second options were wrong ones. And the beauty is the discussion. We discovered rules of IUPAC when we applied them. The last and the least, but 3 ion 1 all and but 4 all 1 ion. Now, there is ein and there is all. There is ein and there is all. What is the way? There is a primary suffix and there is a secondary suffix. Een and ein are primary suffix and they are attached to the word root. So with but, you should get ein. Ein should be with but because but is the word root, and with word root you get primary suffix which is een or ein, and then after that comes the secondary suffix which is the functional group. So I'm very sorry, all first and ein later even without writing is wrong. Very clearly but 3 ein 1 all is correct. Why? Because een or ein are primary suffixes and they get immediately attached to the word root, and they are followed by functional group if any. Functional groups are secondary suffixes and they come after primary. So but 3 ein 1 all, we don't even have to write the structure. By simply quoting the rule, we can conclude that in A, B, C, D, all these cases, the first one was the correct IUPC name and the second one was faulty. And the major takeaway from this question is, why are the wrong ones wrong? This is what we have discussed. Draw formulae for the first 5 members of each homologous series beginning with the compounds. Okay, and we have compounds A, B and C. Now do you remember what exactly is homologous series? Yes, actually the homologous series is actually a set of compounds or a series of compounds which have same functional groups, exactly same functional group, but which differ from each other only by CH2 groups. So the only difference is you would simply have CH2 groups added, that's it, or CH2 n times. Successive members differ only by one CH2 group, or if you take any 2 members, they will be differing by CH2 n times, means CH2 whole twice, CH2 whole thrice, something of that kind. If this is vague, well, let me offer you something more consistent. First 5 members of A. Now I have carboxylic acid. What has been given to me is formic acid, HCOOH, also called as methanoic acid. How do I get the second acid? I add one CH2. I get HCH2 COOH. This is acetic acid or ethanoic acid. Wow. And then this is HCH2. Now I add one more CH2. Propenoic acid. Old common name is propionic acid, latest name is propenoic acid. And then H1, 2, let me add one more. That is such a stupid thing. You keep on adding CH2 groups. It's not stupid. It's actually the method for obtaining the homologous series. Simply HCOOH, the first member. We insert one CH2. Then we have one more CH2, one more CH2 like this. We keep on getting more and more acids. One more. And what is this? This is pentanoic acid. So, methanoic, ethanoic, propenoic, butanoic acid and pentanoic acid. These are the first 5 members of homologous series of carboxylic acids. Similarly in B and C, if you see, in B you have a ketone, acetone, the smallest ketone, and in C you have ethene, the smallest alkene. Can you write down their homologous series by inserting more and more CH2 groups? I guess we can. Shall we? Let's do that. Well, this was the name, this was the carboxylic acid series, the names. It's a very regular theory, I'm just presenting it to you. This is acetone. Now, if I add one more CH2 group, I'll start getting different members. Acetone also is sometimes called propanone by 1, 2, 3. The carbon chain contains 3 carbons, so propanone. 1, 2, 3, 4, butanone, and ketone appears on number 2, so butane 2-one. Similarly, you have pentane 2-one. What I'm doing, I'm just adding CH2 groups here. similarly, just because we were afraid of making this too long, so we have just added one more CH2 here, one more CH2 here. But overall, these have been the groups, and these are the ketones. As simple as this. Ethene, the first member. You add one CH2, like you had this ethene, H, CH, CH2. Now add H, CH2. Now this HCH2 is nothing but CH3. This CH3 which you see here is nothing but this thing. Okay. Now you have one CH3. Now we add one more CH2. Then one more CH2. Then one more CH2. Keep on adding more and more CH2s, and you keep on getting more and more members of the homologous series. It's as simple as this. Give condensed and bond line structural formulas and identify the functional groups present, if any, for A, B and C. Wow, what is this? Let's take a look. A, we are supposed to write down bond line and condensed structural formulas. What is bond line formula? What is condensed structural formula? Well, see, one long or expanded form is you write down every carbon, every hydrogen, H, H, H. Then it's carbon and then again carbons. You go on writing it. That's very expanded or detailed formula. Condensed form would be when you don't make such a hue and cry about this. And bond line notation is very simple. What do you do in bond line notation? You simply make lines, straight line. One carbon-carbon bond is represented by a straight line. Hydrogens disappear. We assume that whatever are the remaining valencies, they will be specified by hydrogens. Every carbon is a corner. Every corner is a carbon. That's it. Heteroatoms like nitrogen, oxygen, etc. are clearly mentioned. Every corner is carbon, and hydrogens, as per requirement, just for satisfying valencies, we assume that students of chemistry at least know how many hydrogens would be there. They just eat it away. That sounds odd. We'll explain you. I'll give you more examples just to make you more comfortable with that. But first, let's do these. 2,2,4-trimethyl pentane. Now, 2,2,4-trimethyl pentane, or anything you want to draw, see, bond line is the simplest. First, we'll start with the word root, pent or ane. So, we need 5 carbons. 1, 2, 3, 4, 5. Every corner is a carbon. That is the concept of bond line. And then we have 1, 2, 3, 4, 5. For your convenience, I have numbered this, otherwise numbering is not necessary. 2, 2, 4. So you have 2 methyl groups and 1 methyl here. This is the bond line notation for 2,2,4-trimethyl pentane. Right. What else? We also wanted condensed formula. What is condensed formula? I'll just write it and show you. Like I have CH3 groups, right? This is CH3, this is CH3, this is CH3, and this is one carbon. Now, how do we write this in condensed formula? We say it is CH3 whole thrice carbon. CH3 whole thrice carbon. Now, this is attached to CH2. C, then we have CH2. And then we have, this is CH. So, we have CH. Now, whenever there is a side chain, in condensed formula, we simply put a bracket. It is CH3, CH, this is CH3 whole twice. CH3, CH3. This is how we write it. This is the condensed formula, and it earlier was bond line notation. Of course, now it is no longer, but then if you want to make it bond line, I can help you out here. I'll just erase the names. I'll just do it again only, that's much simpler. That would be the bond line notation. This is bond line. I draw one here, one there, it doesn't matter, anywhere you want. A is done, now B. Such a long name. It's okay, let's look at the end. It is propane. Then we have tricarboxylic acid. At least we get propane. If we get propane, so we understand that there has to be a carbon chain of 3 carbon atoms. That would be, well, 1, 2, 3. 1, 2, 3 carbon atoms. Lovely. Now, I have 1, 2, 3 propane tricarboxylic acid. That means I have 3 COOH groups attached to it. So, I will take COOH, COOH and COOH. Oh wow. And I have 2 hydroxy. So if this was 1, this is 2, this is 3. So 2 also has OH. Fascinating. So what is this? Is this bond line notation? Not exactly, but I've just written this just for my reference. Now I'll just write down the condensed and bond line both. We'll start with condensed. Fine. We have a COH group. So we have a COOH group. And this is attached to 1. 1 is how much? CH2. So COOH being attached to CH2. COOH, then we have CH2, and then now we have only one carbon C which is attached to OH and COOH. COH, COOH. Side chains are written in brackets. Simply that is condensed formula. And then we have another CH2, which is CO, which is again attached to COH. So we have COH, CH2 one carbon, then second carbon which is attached again to OH and COH. Since they are side chains, they are just put in round brackets one after the other, and then we have CH2 COH. This is the condensed formula. What about the bond line notation? This can be slightly improved, and I will get the bond line notation also. How exactly? Let me do it for you. Now this is COOH. This is COOH. This is OH, which is fine, and this is COOH, right? In bond line notation, the care is we are not explicitly writing down carbons. This is not a bond line notation, strictly speaking, because I have explicitly mentioned carbon atoms. So just to make it more pure, I just improved it like this. This was just for my rough work and reference. I'm just erasing it out. That's it. And this is old questions. I'm again removing it. This was second part. Third one. Third is the easiest. Hexane dial. Oh my God. What does it say? What is hexane dial? Let's see. Hexane means 6 carbons. 1, 2, 3, 4, 5, 6. Dial. It is double aldehyde. Aldehyde is only at the end. Oh wow, 1, 2, 3, 4, 5, 6. Is this hexane dial? It is. This is the bond line notation. Fascinating. And what about the condensed formula? You could also write it. It is CHO. That is aldehydic group. Fine. And then you have CH2. CH2. If you want, you could write it 1, 2, 3, 4. 4 times and CHO like this. If you are more enthusiastic, you can go on repeating CH2s. That is not advisable. Just write it like this. This is the condensed formula. Identifying functional groups is very crucial in organic chemistry. If you are learning organic for the first time, you have to by heart all the groups, their symbols, their names and their structures. Let's begin. You are supposed to identify functional groups in the following compounds, and you have CHO. CHO is actually this group. CHO. This is the structure. This is called an aldehyde. It's an aldehydic functional group? Yes. This is OMe. Structure is OMe. It is like this. And this is an ether. Wow. So we have an aldehyde as well as an ether. Yes. And this is OH. Indeed. OH is alcohol? No, it is usually alcohol. But when this OH is attached to benzene ring, this OH is called phenol. It has a phenolic OH group or a phenolic group. This is what we will say. So we have phenolic group, we have ether, we have aldehyde. This is the list of functional groups present in compound number 1. What about the second one? Let's take a look. We have an amine, and that too a primary amine. Simple NH2 group is called primary amine. Okay, and what about this? We have COOR group. This is called ester. This is called ester. It is Easter. No, Easter is a Christian festival. That's different. This is called ester. Do we have something else? Yes. There is a heteroatom nitrogen. We have CH2, CH2N, and then we have ethyl. What is ET? This ET is equal to C2H5. Ethyl group. In shortcut, it is written as ET. We will write it like this. So this actually, my dear, is a tertiary amine. I have a primary amine, I have a tertiary amine, and I have an ester. These are the 3 functional groups present in the second compound. What about the third one? Let's take a look. It looks much simpler, is it? It is, well, benzene ring, fine. Then you have C double bond C, and then you have NO2. So 2 different functional groups. One is alkene. Many a times there are people who say that alkenes, alkynes should not be classified as functional groups because they are used in primary suffixes, vagara, vagara. It's very much a functional group, alkene. It decides many characteristics of the given substance. And NO2 is nitro. Wow. Nitroalkene, yes. This is it. These are the 2 functional groups present in the poor compound. Which of the 2, NO2, CH2, CH2O minus or CH2, CH2O minus is expected to be more stable, and why? Before we answer this, I guess it will be useful if we make their structures and compare. We have NO2, CH2, CH2O minus, and we have H, CH2, CH2O minus. They are being compared and the stability has been questioned. How do you compare these 2 actually? Well, most of the molecule is same, and the difference lies in only the end, the tail end. Hydrogen has been replaced by NO2 group. And do you see that as compared to hydrogen, nitrogen, oxygen, NO2 group as such is more electronegative? Yes, it has a stronger minus I effect. What? Let me write it down. Minus I effect. It exerts an electron withdrawing effect. Yes, it does exert an electron withdrawing effect. And if there is already a negative charge present, this negative charge, the rule is negative charge is stabilized by what? By electron withdrawing groups. Electron withdrawing groups. Okay, and positive charge must be stabilized by electron releasing groups? Yes, it is. As simple as this. If you have more, give it to me. If you have less, I'll give you. That's a simple rule in organic chemistry, and that is the thing which increases stability. Okay, so we have it. We have it. So which is more stable? 1. This is more stable. This is more stable, and the reason is electron withdrawing groups withdraw electron density away from oxygen atom, because of which electron cloud is spread over larger volume, the charge is spread over larger volume, then it is always more stable. It's a very fundamental rule of organic chemistry. Greater the volume on which charge is spread, more is the stability. That's it. Explain why alkyl groups act as electron donors when attached to a pi system. Very beautiful, very interesting question. And this is something which talks about a term called as hyperconjugation. The way it happens is this. See, if you have a C double bond C system, for example, let us consider propene. The simplest example is propene. CH3, CH double bond CH2. Now, I have a methyl group which is attached to a pi system. Is that fine? Yeah. Now, can I draw ethene first? Well, if you just care to draw the structure of ethene, I'm just trying to draw this in a plane, that's it. The way you visualize this is the plane of molecule, these are the sigma bonds. I'm just talking about ethene for the time being, and then there's a pi bond here. I mean, it's an overlap, fine and all that stuff. Some portion is below. I mean, this is above the plane, we can see it, it's below the plane, we can just see some part of it. That's how we visualize this. So this is the sigma bond, this is pi bond, this is C double bond C. Alright. Now, what they're saying is, if an alkyl group gets attached, so one of these hydrogens I'm going to replace by a methyl group. And let's see what happens. Let's say this one looks more spacious, so let me just change this. Say if this becomes C, H, 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 what happens? Please understand, if you visualize this methyl, can you visualize this as an umbrella? Umbrella, yeah. It's not a planar molecule. I mean, if one of these groups is on this, the second group would be protruding away in the direction of pen, and the third group would be actually pointing inward inside the board, which obviously I cannot poke my pen inside the board and show you. But then this is the way we denote it, by a cut line like this. I'll remove the earlier hydrogens. Yeah. So actually, the methyl group it's more like, just visualize my hand. It's like this. I mean, I have 5 fingers. There are only 3 groups. Imagine 2 fingers are missing, God forbid. But then, I mean, it's like this. And it's like a fan. So it's rotating always like this. So, although the fan has 3 blades or 4 blades, usually, if it rotates, what you see is roughly like a disc, right? In the same fashion, if this rotates like anything very quickly, I can't, this hand is bound, it's not free, I can rotate it, but if this keeps on rotating like this, then ultimately what you would see? You would be able to see this is something like a cone. It is more or less like a cone. So these bonds, because they are very quickly and happily rotating around this line. Oh my God, this got erased. Let me bring it back. Yeah, they're rotating like this. If it is rotating like this, so what I have is I have a cone of electrons. On this cone, hydrogen atoms are moving. And just like if a rotating fan, if you observe, you would be able to see something like a disc, although there is no actual disc. In the same fashion, when this fan-like structure rotates, you get a cone. And this cone has electrons, CH bonds. That means it contains those electrons, right? So electrons are on the surface of this cone. The bonds are on the surface of this cone. Please note that. And this electron cloud overlaps like this. Oh my God. That is the case. Yes, it overlaps like this. If you are doing it as per MO theory, molecular orbital theory, you could be actually more fashionable and you can say that pi star orbitals overlap this. Otherwise, in valence bond theory, you simply show that this kind of an overlap occurs. And because of this overlap, you find, and why does this happen? Why is it that, these electrons are attracted away from methyl group? It is because in methyl group, please note, CH3 is sp3 hybridized. And these are sp2 hybridized. sp2 hybridized carbon is more electronegative than sp3. Okay, Very interesting. So you find that difference is small only, but these methyl groups tend to give away their electron cloud. The advantage being the electron cloud is now spread over larger volume. And the basic rule of chemistry is the greater the volume on which the charge is spread, more is the stability. So this, my dears, is also known as, well, if you want it in full glory and style, it is called sacrificial hyperconjugation. Let's cut the nonsense. Let's call it simply hyperconjugation. Yes, it is. And this is the way we write it. So that is the reason why alkyl groups act as electron donors when attached to a pi system. Now this is a long question. It says draw the resonance structures for the following compounds. Show the electron shift using curved arrow notation. Okay. So, and please note, this is a very fundamental exercise in organic chemistry. You will always need it. So let us start drawing. I'll advise you, in case you feel lazy about it, you have to draw this thing nicely and properly. If you try shortcuts in this, you will always have problems when it comes to learning organic properly. So my very sincere suggestion, please don't try shortcuts with this. You must write it down nicely. What are you up to? I am just writing down the skeleton structure of phenol. What do you mean by the skeleton structure? I am just writing down sigma bonds. I am not writing down lone pairs. I am not writing down the pi bonds. Fine. First I have made this. Of course, phenol in the full glory is this. These are not the final structures, but I am going to draw more. What happens? You find the way when you are trying out delocalization, this jumps and it shifts here. Please note, if the lone pair is getting delocalized, the arrow must begin from lone pair. And it is converting to a bond, so arrow must finish in the middle of this bond. So this is how I am going to draw this. And since this pi bond jumps away, so this arrow should start in the middle of the bond and the arrow must end at the corner, because this is where the lone pair has to come. Oh my God, that way, yes. What about these two? These two are not changed. They just remain as they are. This is curved arrow notation. Yes, yes, this is curved arrow notation, and this is how we do the delocalization. Okay. Sometimes people encircle it so that the electrons are not lost. Otherwise, it's not necessary. I'm just copying, this is the old stuff, and I get something new here. Yes. And what happens then? This can jump up like this, and this can come back here. Right? And the last step, well, the mummy returns. This is what you get. Now, please note, first and last are not the same. Why? Double here, it's only single here. So, if benzene ring you rotate, you will get 1 and 5. 1 and 5 are equivalent structures. They have same energy, but they are not same. Please note. These are the 5 structures, contributing structures of phenol. Now, B is a group which is an electron withdrawing group, NO2 group, and let us see how does B fare. Let's take a look. Well, we have benzene ring being attached to NO2. My dears, first of all, please learn this is the structure of NO2 group. This NO2 group you can attach anywhere you like this. This is NO2 group. So every time you don't start discovering NO2 from zero, it is easier to just learn it like this, right? And now, when we have this NO2 group, how does it behave as an electron withdrawing group? So, it takes away electrons from benzene ring like this. Oh wow! Now what happens? Well, I have N, I have plus here like this. Nitrogen retains its formal plus charge always, that's okay. I have now a plus charge on benzene ring. What next? Well, nothing great. life is a full circle, so it keeps on rotating. It moves to ortho and then it is moving to para. I hope you can see that. Very typical gesture of delocalization in the benzene ring. One more. And what do I get? I get once again a positive charge on ortho location. Please note, it has not touched meta location. It's like ortho, para, ortho, and then back again. Back again would be, well, this can come back and this can go here. So what do I get? I would get N O like this. I have 1, 2, 3, 4, 5. That's quite phenol-like. Is it all? No, there is a special catch. Now please note that in these two, in number 2, 3 and 4, you have NO2 minus like stuff here. It's okay. But in 1 and 5, do you see that internally also a delocalization is possible? What does that mean? I'll just show you here. I don't have a space there, so I'm writing here. I'm just copying 1 as it is. Please note 1 and 5 are not same. Double here, single here. Benzene ring has rotated in 1 and 5. 1 and 5 are not same. They have same energy, but the structures are different. Now, instead of double single, I could have written double here and single here. Right? Like this. So, I also have 6 and I also have a 7th structure. 5. What is? That means I'm just changing spaces, places of double and single bond in NO2 group. Ping tang. So I get 7 contributing structures, my dear, for nitrobenzene, like this. Now when we see C and D, benzene ring with CHO. Now CHO group is very similar. And let's skip C for the time being, we'll come back to C. But I think it will be much easier if we finish D now itself. Shall we? Yes. There is a hint. See, this is NO2 group. Right? CHO is like this. Instead of this O and lone pairs, I just have H. But the bond is single. Instead of N, I get carbon and there is no plus charge. This is a difference. And this is the similarity also kind of. What do you wish to say? I wish to say that I'm going to convert these structures of NO2, nitrobenzene to benzaldehyde. Watch. It's a very good trick. I'm just getting rid of these nitrogens, lovely though they may be. But of course, there's not going to be any plus charge on them, very much. Yeah. Now, also that O minus is no longer needed. I will have a hydrogen here. Okay. So you're removing this? Yeah. In the same effort, you can actually redraw this. Then why are you not redrawing? I've drawn it thousands of times. Don't worry about me. I'm just trying to show you a similarity between different structures. Essential structures are A and B only. All other structures, my dear, you will note are just variations, nothing new. Like, let me come to this. See, you have, just put CHO. This is benzaldehyde. Yeah. Benzaldehyde, benzaldehyde, benzaldehyde and benzaldehyde. Fascinating. These are the 5 structures of, benzaldehyde. You have it here. But you skipped C. C also, you will notice, is very similar and much easier than D. But D was very easy. C is even easier. How is it? I'll tell you how is it. Just wait for a moment. Let me clean some space. I'll solve it for you here itself. Why you could use another page? No. I just wish to compare. And this comparison would be very useful and very enlightening for you. That's why I'm just trying to use the same space on the same page so that we are also on the same page, literally. right? See, take a look. This is CH3, CH, double bond CH, CHO. It is like this, right? Now, if you just compare, well, I could have also drawn it in a different style. I could have just drawn it like this. This is compound C. Do you see that this is not very different from L? Yeah. So this is one contributing structure. I can write it like this, or I could just make it jump, yeah, and write it like are these the contributing structures? Yes, these are the contributing structures of course C. Oh my God, that's it. That's it. What about the top one? No, the top one is not there. It is just same as, I mean, this is nothing new. 1, 2 and 3. And this is all, these are the contributing structures of C. So I hope you can see that we have covered A, B, C and D till this point. And let's turn to E and F. I've just made some skeletons so that we save some time for quick structure writing. It is benzyl cation. This E part was benzyl cation. It is this. And, well, pi bond, shadak. It goes that side. I get CH2 here and a plus charge here, of course. And this plus charge can again go on this side. Well, this is very benzaldehyde-ish. Indeed it is. And it just keeps on and on. The fun never stops, literally. And this is all what we get. We get 5 structures for benzyl cation, like this. 1, 2, 3, 4, 5. What about the F part? F part is even simpler. F part contained this. 1, 2, 3, 4. Butynyl cation. Okay. Then just jump it. Yeah, make it jump. That's all. That's all. These are the 2 contributing structures for F. What are nucleophiles and electrophiles? Explain with examples. Oh my God, this is a theoretical question and you will need a written theoretical answer. So I've got this written for you, but nonetheless, I'll also put it verbally also. Electrophiles, phile means loving. Electrophiles means the species which love electrons. Electron loving species. I mean, these naturally are the species which are, you can say not very electron rich, in fact electron deficient species which approach those species which are electron rich. So typically cations or species which have incomplete octet or the species which are asking for a donation of electrons from anyone. Lewis acids, yes, they are electrophiles. They are electron loving species which are electron deficient in nature. They can accept electron pairs from electron rich species and they are in that sense also called as Lewis acids. Examples, you could have neutral molecules with empty orbitals, incomplete octet, AlCl3, BF3, FeCl3, permanent beggars and they are all electrophiles. Or you could have cations, chloroniamine, bromoniamine, nitroniamines, carbocations. Wow, they are electrophiles. They are fantastic electrophiles. Fanciful. What about a nucleophile? Nucleophile is nucleus loving, anything which loves a positive charge. Okay, they are typically electron rich species. So they are looking for somebody who can accept some electrons so that they can stabilize themselves by donating some set of electrons. So they are electron rich species and they donate electron pairs to electron deficient species. They are really good. Yes, they are indeed. And please note, this donation has to be a coordinate covalent bond. It should not be a redox reaction, right? Okay. What are the types of nucleophiles? Typically, if you have a lone pair and you are willing to donate, you are a nucleophile. So negatively charged species like carbanions, cyanide, halide ions, oxide ions, OH minus, RO minus, these are fantastic nucleophiles. What else? Well, there could be other neutral species like ammonia, water. They also have lone pairs. So not just anions, neutral species also have lone pairs and they may also donate. Both of them are nucleophiles. Please note, if lone pair is present on a species which already has a plus charge, then they are not considered as nucleophiles. Why? Because they already have a plus charge. So they will not be attracted to another positive charge, right? That way.